Today, we're examining how to solve a quadratic equation that doesn't appear in the form we typically see in algebra class. Here's our equation. 7 plus 25 times the quantity 2x plus 3 squared equals 0. Notice how this doesn't look like the typical x squared plus bx plus c equals 0 format we're used to. The key to this problem is understanding what's happening with this squared binomial term. Instead of having x squared directly, we have a more complex expression squared, which will require special handling. When we see a non-standard form like this, we shouldn't immediately try to expand everything. Instead, we should look for a more elegant approach that takes advantage of the squared term structure. The presence of this squared binomial suggests we can solve this equation without having to fully expand and factor. We'll see how this approach can be much more efficient. We're all familiar with the standard form, ax squared plus bx plus c equals 0, where we can apply the quadratic formula or factoring techniques. Our equation doesn't immediately fit this pattern. While we could try to expand our equation to match this standard form, that would involve distributing the squared term and potentially creating more complicated numbers to work with. Looking at the differences, in standard form, we have a simple x squared term, while our equation has this 2x plus 3 squared term. This structural difference will guide our solution strategy. We'll isolate this squared binomial rather than expanding it. Let's clear the screen and focus on solving our equation. We'll take advantage of the structure to find a more elegant solution than simply expanding everything. Our approach will be to isolate the squared binomial term first, then work with that to find the values of x that make the equation true. When dealing with equations like this, we want to isolate the squared term and then take the square root of both sides. This is much simpler than expanding the entire expression. We're starting with the equation 7 plus 25 times 2x plus 3 squared equals 0. This is a quadratic equation, but it's not in the standard form we're used to seeing. To begin solving this equation, we need to isolate the squared term containing our variable x. This will make it easier to eventually solve for x. We'll subtract 7 from both sides of the equation. On the left side, 7 minus 7 equals 0, leaving us with just 25 times 2x plus 3 squared. On the right side, 0 minus 7 gives us negative 7. Notice that when we move a term from one side of the equation to the other, its sign changes. The positive 7 on the left becomes negative 7 on the right. This is because we're performing the same operation to both sides of the equation, subtracting 7. Now we have 25 times 2x plus 3 squared equals negative 7. The squared term containing our variable is isolated on the left side, which makes it easier to proceed with solving for x. This step of isolating the squared term is crucial for solving quadratic equations in this form. It allows us to more easily apply the square root property in the next steps. In our next step, we'll need to isolate the expression inside the parentheses, which is 2x plus 3. We'll do this by dividing both sides by 25 and then taking the square root. Let's continue with our quadratic equation. We have 25 times the quantity 2x plus 3 squared equals negative 7. To isolate the squared binomial term, we'll divide both sides of the equation by 25. This is a crucial algebraic move that will simplify our equation significantly. Let's highlight the terms involved in this division. We have 25 in the coefficient on the left being divided by 25 and negative 7 on the right also being divided by 25. When we perform the division, the 25 on the left side cancels out completely, leaving just our squared binomial. On the right side, negative 7 divided by 25 gives us the fraction negative 7 over 25. Notice what we've accomplished here. We now have a perfect square expression on the left side, the quantity 2x plus 3 squared. This is exactly the form we want when solving quadratic equations using the square root method. However, we have an interesting situation because our perfect square equals a negative fraction on the right side. This introduces a critical mathematical consideration. Let's examine this structure carefully. We have a perfect square expression equal to a negative value. In algebra, this is a significant observation because perfect squares in the real number system are always positive or zero, never negative. This raises an important question. Can the square of a real number ever equal a negative value? The answer is no, which means our equation won't have real number solutions. Any number squared, whether positive or negative, always results in a positive value or zero. This reveals something fundamental about our original equation. Since we've determined that a perfect square cannot equal a negative number in the real number system, our equation 7 plus 25 times the quantity 2x plus 3 squared equals 0 has no real solutions. We're looking at the equation 2x plus 3 squared equals negative 7 over 25. This is an interesting case because we have a squared term equal to a negative number, which will lead us into the world of complex numbers. To solve for x, we need to isolate it. The first step is to take the square root of both sides. Remember that when we take the square root of a squared term, we need both the positive and negative values, which gives us 2x plus 3 equals plus or minus the square root of negative 7 over 25. But wait, there's a problem here. We have a negative number under the square root. In the real number system, we cannot take the square root of a negative number because no real number multiplied by itself gives a negative result. If we square any real number, the result is always positive or zero. To solve this equation, we need to extend our number system beyond the real numbers into what mathematicians call complex numbers. These allow us to work with square roots of negative numbers in a meaningful way. The foundation of complex numbers is the imaginary unit I, which is defined as the square root of negative 1. This is a new type of number that doesn't exist on the real number line, but allows us to express the square roots of negative numbers. From this definition, we can see that I squared equals negative 1. This is the fundamental property that makes complex numbers work. It gives us a way to represent and work with quantities that couldn't be expressed in the real number system. Using the imaginary unit, we can establish a general rule. The square root of any negative number, negative a, can be rewritten as I times the square root of a, where a is positive. This allows us to separate the negative sign from under the radical. Applying this rule to our equation, we rewrite the square root of negative 7 over 25 as I times the square root of 7 over 25. The square root of 7 over 25 is a real number, and multiplying it by I makes it an imaginary number. This expression is our solution in terms of complex numbers. To find the actual value of x, we would subtract 3 from both sides and divide by 2, which would give us x equals negative 3 over 2 plus or minus I times the square root of 7 over 50. These are two complex number solutions to our original quadratic equation. This example demonstrates a key concept in algebra. When a quadratic equation has no real solutions, it will have complex solutions instead. The quadratic formula will always give you the correct solutions, even when they involve complex numbers. In our previous work, we ended up with this equation: 2x plus 3 equals plus or minus the square root of negative 7 over 25. Now we need to simplify this complex expression to a more standard form. When working with the square root of a negative number, it's helpful to rewrite it by factoring out negative 1. This allows us to use the properties of complex numbers. So we rewrite the square root of negative 7 over 25 as the square root of negative 1 times 7 over 25. One of the fundamental properties in complex number theory is that the square root of negative 1 equals I, the imaginary unit. So we can apply the rule shown here. The square root of negative 1 times a number equals I times the square root of that positive number. This transforms our expression into 2x plus 3 equals plus or minus I times the square root of 7 over 25. Now we can further simplify by applying another property of square roots. The square root of a fraction equals the square root of the numerator divided by the square root of the denominator. This gives us I times the square root of 7 divided by the square root of 25. Since the square root of 25 equals 5, we get I times the square root of 7 over 5. For our final expression, we can rearrange slightly to write it as 2x plus 3 equals plus or minus I times the square root of 7 all over 5. This is the conventional way to express complex number solutions. I've highlighted the imaginary unit I in red to emphasize that our solutions will be complex numbers, not real numbers. This form is significant because it clearly shows we're working with complex values. When we encounter expressions like this in the context of quadratic equations, it indicates that the parabola representing our original equation never crosses the x-axis, which is why we don't have any real number solutions. The presence of the imaginary unit I is what makes these solutions complex. In our original quadratic equation, 7 plus 25 times the quantity 2x plus 3 squared equals 0, we've now found that the expression under the square root is negative, which is why we needed to introduce complex numbers to find a solution. To complete our solution, we'll need to solve for x by isolating it in our equation. This will give us the exact complex solutions to our original quadratic equation. We've arrived at this intermediate step in our solution, where we have 2x plus 3 equals plus or minus I times the square root of 7 over 5. Now we need to solve for x by isolating it on one side of the equation. To isolate the term with x, our first step is to subtract 3 from both sides of the equation. On the left side, 2x plus 3 minus 3 gives us just 2x. On the right side, we get negative 3 plus or minus I times the square root of 7 over 5. Now that we have 2x on the left side, we need to divide both sides by 2 to isolate x. When we divide the left side by 2, we get just x. On the right side, we need to divide the entire expression by 2, which gives us negative 3 plus or minus I times the square root of 7 over 5, all divided by 2. Let's simplify this expression to make it clearer. For the first term, negative 3 divided by 2 is negative 3 halves. For the second term, we need to distribute the division by 2. When we divide I times the square root of 7 over 5 by 2, we get I times the square root of 7 over 10, because 5 times 2 equals 10. This gives us our simplified expression. Since our equation contains a plus or minus symbol, we actually have two distinct solutions. We can write them separately as x sub 1 equals negative 3 halves plus I times the square root of 7 over 10, and x sub 2 equals negative 3 halves minus I times the square root of 7 over 10. These are our two complex solutions to the original quadratic equation. Notice that they are complex conjugates of each other, which is a pattern you'll often see when solving quadratics that don't have real roots. The real part is negative 3 halves for both solutions, while the imaginary parts have the same magnitude but opposite signs. The original equation 7 plus 25 times the quantity 2x plus 3 squared equals 0 has these two complex solutions. This makes sense because when we graph the original function, it never crosses the x-axis, meaning there are no real values of x that make the equation equal to 0. Complex solutions like these appear in many applications in physics, engineering, and signal processing, where they help us understand oscillatory behavior and wave phenomena. In this example, we've seen how to solve a quadratic equation that yields complex solutions by properly isolating the variable and simplifying the resulting expression.